stationary points are extremely useful components in graph sketching and a good direct application of differentiation. Now, before we say what it is, let's first understand what it means for a function to be increasing or decreasing. And as you could probably guess, a function is increasing if it's getting bigger or decreasing if it's getting smaller. So if we look at this graph, we see that for this green part here, the graph is increasing, and in the red part here, the graph is decreasing. Then it's increasing again, as we see from this green part here, where the function is getting bigger again. But at the exact point where the function has stopped increasing or decreasing and is transitioning into decreasing or increasing, we call this point a stationary point. Now, this stationary point is called a maximum stationary point, or just maximum point, and this point here is called a minimum stationary point, or just minimum point. Don't get confused though, a maximum stationary point doesn't mean the largest stationary point on the graph, as we can have multiple maximum and minimum stationary points. So a maximum stationary point occurs when the graph is going from increasing to decreasing and kind of looks like an N shape, and a minimum stationary point happens when the graph is going from decreasing to increasing and looks like a U shape. Now, there is something unique about stationary points that we're going to look at. Take a function represented by this graph here. Now, these two purple points represent the graph's stationary points, and this green line here represents the gradient at the yellow point on the graph. Have a look at what happens as this point traverses through the graph. So first, we see that in the increasing part of the graph, the gradient is positive. And as we get closer and closer to the stationary point, the gradient decreases to 0. And at the stationary point, the gradient is 0. Then when we're decreasing again, the gradient goes negative, but then begins to go back to 0 as we head to the second stationary point, at which we have a gradient of 0 again. And now when we're back into the increasing part of the graph, the gradient is positive and increasing. So we have learnt three things from this. First, we have learnt that when a function is increasing, it has positive gradient. And this double arrow here just means it goes both ways. So if a positive gradient also means that a function is increasing. Now, the second thing that we learned is that a decreasing function has negative gradient and vice versa. And finally, the third and most important thing that we've learned is that stationary points have a gradient of 0. So let's take an example. Suppose that we want to find the stationary points of the function y equals x cubed plus 3x squared minus 9x plus 1. Now, the graph of this function looks like this. And in order to find the stationary points, we need to remember that the gradient is equal to dy dx. So a stationary point has dy dx equal to 0. So for y equals x cubed plus 3x squared minus 9x plus 1, to find dy dx, we use our famous rule of bringing the power to the front and reducing the power by 1. This gives us dy dx is equal to 3x squared plus 6x minus 9. This means that we want 3x squared plus 6x minus 9 to equal 0. And solving this, dividing both sides by 3, we get that x squared plus 2x minus 3 is equal to 0. And factorizing, we have that x plus 3 times x minus 1 is equal to 0. This gives us that x is equal to minus 3 and x is equal to 1. And to find the corresponding y coordinates of the stationary points, we just substitute in our x values into the original equation. So when x is minus 3, we have y is equal to 28. And when x is equal to 1, we have y is equal to minus 4. So the stationary points are at minus 3, 28 and 1, minus 4. Now if we go back up to the graph here, we see that we have two stationary points. And the first is obviously minus 3, 28. And the second is 1, minus 4. Now the point at 1, minus 4 is a minimum stationary point. And the stationary point at minus 3, 28 is a maximum stationary point. Now usually we don't already have a sketch of the graph in order to determine which stationary point is minimum or maximum. In fact, we try to find stationary points to help sketch a graph. Now we know dy dx is equal to 0 when there is a stationary point. But how do we know whether it's a minimum or a maximum point? Now both minimum and maximum points are stationary points, so we need a way to distinguish between the two. Now there are two ways of doing this. The first is by checking nearby points. So let's take our original equation again, and like before, we find out that our stationary points are minus 328 and 1 minus 4. Now let's focus on the point minus 328, and let's plot this point on a graph. Now consider a point that's just to the right of this point. So take x equal to minus 2.9. Now substituting this into our equation gives y equal to 27.941. Now let's plot this coordinate on the graph here, and now let's consider another point that's just to the left of our stationary point. Let's take x equal to minus 3.1. Substituting this into our equation, we get y is equal to 27.939. Now let's also plot this point on the graph below. Now let's draw a curve through the stationary point and these two nearby points. And now what we've actually done is drawn part of the graph of the equation near the stationary point. And we see that this part of the graph is N-shaped. Therefore, minus 328 is a maximum stationary point. Let's now consider the other stationary point, 1 minus 4. And again, let's consider a nearby point that's just to the right of this point. Let's take x equal to 1.1. Substituting this into our equation, we get y is equal to minus 3.939. Now let's plot this point on the graph and let's consider a point just to the left of the stationary point. Let's take x equal to 0.9. Substituting this into our equation, we get y is equal to minus 3.941. Now let's also plot this point on the graph, and finally let's draw a curve through all of these points. Now we see that we have a U-shaped graph, which means that this point is a minimum stationary point. Now this method is quite tedious and almost surely requires a calculator to be accurate with it. Now there's a better, more slick method for finding maximum minimum stationary points, and that method is the idea of using the second derivative. Now as a quick side note, the first derivative is written as dy dx, which can also be written as d dx of y. Now the second derivative is the derivative of the derivative, or the gradient of the gradient, which is d dx of dy dx. Now removing the brackets gives us d dy over dx dx, and since there are two d's in the numerator, we can write this as d squared, and since there are two dx's in the denominator, we can write this as dx squared, and normally we omit the brackets and just write dx squared. Now this is how we write the second derivative. Now consider the graph near any maximum point. Now the green line is the gradient at the green point. And let's plot the values of dy dx on a graph. So at the beginning, the gradient is positive and then goes towards 0 and then turns negative again. Now the function we have drawn is dy dx, and the gradient of this function is negative. That means that df by dx, which is equal to d dx of dy dx, and we know that that's just our d squared y over dx squared, is less than 0. And this gives us the famous rule that if the second derivative is negative at the stationary point, then it is a maximum stationary point. Now let's consider the graph near any minimum point, and let's again plot the gradient, or dy dx, on a graph. We see at first that the gradient is negative, and then it goes towards 0 and then becomes positive. Now the function we have drawn is dy dx, and this function has a positive gradient. That means, like before, that d squared y over dx squared is bigger than 0, and this gives us the famous rule that if the second derivative is positive at the stationary point, then it is a minimum stationary point. So let's now apply what we've learned to our original equation. Remember, we had y is equal to x cubed plus 3x squared minus 9x plus 1. And like before, we had the stationary points minus 328 and 1 minus 4. Now dy dx is equal to 3x squared plus 6x minus 9, and now the derivative of that would be d squared y over dx squared, which is 6x plus 6. Let's now substitute in the first coordinate of the first stationary point. So let's substitute in x equals minus 3. We get that d squared y over dx squared is equal to minus 18 plus 6, which is equal to minus 12. And since d squared y over dx squared is negative at x equals minus 3, then minus 3/28 is a maximum stationary point. And subbing in the second coordinate x equals 1 of the second stationary point, we have that d squared y over dx squared is equal to 12. Since d squared y over dx squared is positive, then it is a minimum stationary point. So clearly you see that this method is a lot better than the previous method and a lot quicker. So we have two methods of finding stationary points. And with the second method in particular, we have that if the second derivative is negative, then it is a maximum point, and if the second derivative is positive, then it is a minimum point. But what would happen if the second derivative is equal to 0? If this actually happens, then we cannot use this method, and we have to use the method of nearby points, because when the second derivative is equal to 0, it could be a maximum, it could be a minimum, or it could even be something called a point of inflection. Now, a point of inflection is where a curve goes from positive gradient to 0 gradient, where there's a stationary point, to positive gradient again. Or it's a curve that goes from negative gradient to a stationary point to negative gradient again. And this isn't rare, as great examples of this is y equals x cubed and y equals minus x cubed, which are the two curves that we have drawn. Now, inflection points can only happen when d squared y over dx squared is equal to 0 at a stationary point. But if d squared y over dx squared equals 0, this doesn't mean that it is an inflection point. So it works one way, but doesn't work the other way. And the best way to see this is to take a look at y equals x to the power of 4 and take a look at the stationary point at 0, 0. I'll let you guys try this one out for yourself. Now, for more questions and answers, check out our problem sheet in the description below. So if you liked the video, be sure to drop a like on it and hit that subscribe button if you want to learn, explore and master more mathematics. And head over to mathesy.com where you can find all my notes, my videos, and if you want to support the channel. Hope you guys have a good day, and I'll see you all next time.